Hello, myself Neelab Sinha, on behalf of my team consisting of Michael Balazia and François Bremont, will be going through our work on facial landmark heat map activated multimodal gaze estimation, or FLAME. The application of the domain of gaze estimation ranges from human computer interaction, analysis of human behavior, clinical diagnosis, gaming design, and even beyond. Formally, we will be dealing with appearance-based 3D gaze estimation, which is about using the eye images directly to infer the line of sight of a person in 3D space. Existing methodologies include person-independent methods, which focus on using distinct samples of subjects in training and test set. This allows estimating gaze without the dependency on any subject-specific parameters. However, eventually it was proven that people's anatomical differences limit the performance of these methods significantly. This allowed the research to move in the direction of person-specific methods, which focus on introducing different ways of subject-specific calibration techniques to learn these anatomical features effectively using a small portion of test set. However, when designing a practical systems, these methods pose significant limitations. In case of person-independent methods, they do not take the inter-subject differences of anatomy into account and thus lack precision up to an acceptable range. On the other hand, for person-specific methods, we need to have accurate calibration samples of test subjects, which poses different challenges in different applications and thus impacts scalability. Keeping in mind these limitations, we have developed this work, which proposes a novel approach of fusing anatomical features of the subjects with the RGB features without any calibration for a precise gaze estimation. We propose to do this by extracting these features from 2D eye landmarks obtained from RGB images themselves. These landmarks hold key information about anatomy of the eye and also are strongly correlated to gaze. However, as extraction of these landmarks may be prone to errors, instead of using them directly, we propose to use it in the form of Gaussian probability distribution heat map. This approach makes the model robust to such errors. We conduct experimentations extensively on two benchmark datasets in person-independent settings to validate our approach. We move to see how to obtain eye landmark heat map. So first we extract face crops from the images and then use OpenFace, a facial analysis toolkit, to get eye landmark coordinates. The reason behind using OpenFace is that apart from the outer boundary, it also gives landmarks corresponding to outline of cornea and pupil, as you can see in this figure. This gives a lot of information about physical structure of the eye. We therefore get 2D coordinates of 28 landmark points. We use it to obtain Gaussian probability distribution heat map for each landmark in a separate channel using the mean as the obtained landmark coordinate itself. So essentially, we obtain a 2D 28 channel heat map, each for one landmark and of the same height and width as that of the input image. To cover our complete architecture, we first randomly extract 120 cross 120 eye crop from either the left or the right eye from a sample, which we will refer to as R, along with corresponding heat map, which we will call H. We pass both of them through separate, parallel, yet identical CNN backbone made up of residual blocks, as we can see here. We use a relatively shallow backbone because we believe gaze is a low level feature and thus such kind of a backbone can learn required features efficiently. We allow slow fusion of these features into one another using a transfer function T of R, H, constituting of MMTM blocks after the output of module 2 and 3, as we can see here. We shall cover this in further detail later on. At the end, we aggregate both the features by concatenating them and passing it through a residual block, which we call aggregation function A of R, H. At every point, the dimension of Both feature maps are same which allow us to carry out these operations easily. Then we concatenate this hybrid feature map along with head pose angles and pass it through two dense layers of 512 neurons each to predict gaze angles, pitch and yaw corresponding to vertical and horizontal movement of the eye directly in the world coordinate system. To cover MMTM or the multimodal fusion module developed by Jose et al., it is essentially a slow modality fusion mechanism based on squeeze and excitation. This is valid for any two feature vectors of arbitrary size, but we use it to fuse the heat map feature with the RGB features, which are of identical dimensions. Let us consider the RGB feature vector to be of dimension n cross m cross c of Ri and heat map feature vector to be of n cross m cross c of Hi. We first squeeze them by channel-wise global average pooling to have S of Ri and S of Hi as per these equations. Then these are passed through a dense layer to get joint representation Zi as you can see in the figure. This Zi is then passed through two separate dense layers to obtain excitation signals E of Ri and E of Hi for recalibration of feature maps. The recalibrated feature map is obtained by using these equations by taking sigmoid of excitation values and multiplying it with corresponding channels. This way we allow slow yet effective information exchange between both the feature vectors at intermediate positions. We do to carry out experimentations, we use two publicly available datasets, IDEAP and Columbia Gaze, which are very different in nature. IDEAP is a video dataset, and so we take every 20th frame minute for training and evaluation. We train our model with these set of hyperparameters for 200 epochs. Loss can be measured by the angular deviation of predicted gaze vector GP with the true gaze vector GT using this 3D angular loss. However, if we look at the gradient of this loss, as GP starts coinciding with GT, the dot product starts tending to 1 and so gradient of this loss starts tending to infinite. This makes the model unstable as the loss starts to decrease. So training on this loss is not a good idea. Instead, we propose to use vector difference loss given by sum of squared differences of individual components of the predicted and the true gaze vectors. We use this loss to train our model and the 3D angular loss for evaluations which directly give the angular deviation between the prediction and the truth. We evaluate the performance of our method on both cross-person and cross-dataset settings. In person-independent settings, we obtain an error of 4.62 degrees on IDEAP and 4.64 degrees on Columbia Gaze. For cross-dataset settings, we get an error of 12.53 degrees by training on Columbia Gaze and testing on IDEAP, and 12.83 degrees for the vice versa. This figure at the bottom shows the relation between the truth and the predictions. The upper row is the yaw and the lower is the pitch. We can see that the variation is fairly linear, which justifies the correctness of our method. Comparing our method with different state of the art, our method outperforms all of the person independent techniques and also few person dependent techniques. To analyze the causes of error, we are using actually 2D facial landmarks and not 3D, which gives us a lot but not all information about the eye anatomy. It also does not give the precise orientation of eye in 3D space. Also, the error of obtaining landmarks can be high if the complete eye is not visible in the image due to different reasons. So, these factors can contribute to the error. However, we are still able to achieve competitive performance for both cross dataset and cross subject settings with our proposed approach. We also conduct an ablation study to understand the impact of different elements that we have used in our model. Flame is our proposed methodology. Flame aggregation only or FAO is where we have kept the entire architecture same except for the transfer function using MMTM fusion, which we have removed. We can see that the difference in error is a bit, which which is important to understand the impact of the transfer function. Further, the flame additive fusion, or F of AF, is where instead of using residual blocks for aggregation, we just perform element-wise addition of two modalities after the last layer of the CNN backbone. The difference in error of this and FAO shows how effectively we are able to aggregate RGB and heatmap fusion using our aggregation function. At last, the entire contribution of our architecture and using I landmarks to incorporate anatomical features with RGB can be seen by the difference in error between flame and flame baseline. In baseline, we just use the RGB features and the same CNN backbone to estimate gaze without using landmarks in any form. We also experimented using absolute value of landmarks using various feature extractor, and our heatmap based approach outperforms all of them. So that is from all from our side. Thank you for your attention.